Our Raspberry Pi has a quad-core CPU. Until now, all of our C++ programs were written for a single core. Now we will learn how to use all cores, and we will see how this can improve the speed of our programs. Now it would be nice if I don't go straight into writing programs, but first answer some questions like why do they make multi-core CPUs? Can we use the same old algorithms and just run them on multiple cores? But I'll do that later. So we'll go straight into example. I'm going to give you one example, then solve that example using a single CPU, and then make an algorithm and a program that solves this using all cores, and then we will compare the speeds, and then we will come back to the questions 1 and 2 and give some introduction to all this business. The input consists of a very large integer n, 500,000, and two sequences, alpha and beta, that have 500,000 terms. And the input also consists of some prime number p. We need to create a program that makes a sequence gamma that also has 500,000 terms, and the terms of gamma are created in the following way. Gamma I is alpha I to the power beta I modulo p. We will calculate these powers modulo p by using the following function. There are more efficient ways to calculate a to the b modulo p. We are not going to use a more efficient function. We will use this function. This function will be used both in parallel and non-parallel algorithm. And then we will compare their speeds. Now it is time to turn on the Raspberry Pi. We will open the files and we will open a terminal. We will shorten the prompt of the terminal using the command ps1. Then we will create a folder parallel01 in which we will place all our files. The course website and the link to the website will be in the description of this video. Contains one file and one document that you should copy paste and create a file called simple timer. The file simpletimer.cpp is going to contain the code that we will include in our algorithms, in our programs, and that timer will be used to calculate how long it takes for non-parallel program to finish its execution, and it will also calculate how long it takes for parallel program to do the execution. So we are going to use this code instead of using stopwatch. The program itself will count in seconds, and actually it can do milliseconds. And we will have very good comparison, good way to compare the speeds of two programs. So this is how I accessed the website. I copied the code from that box and I have created the file simpletimer We will create the file non-parallel.cpp that will contain the source for our non-parallel program. After we made sure that the file simpletimer.cpp contains the code from the website and is placed in the same folder as this source file non-parallel.cpp, then we can include simpletimer, then we implement the power function as we described earlier, and we can then start implementing the non-parallel function that creates the sequence gamma. The arguments of the function should be the prime number p and the integer n, and actually my favorite way is to write first the prime number p and then n. So I will decide later that this long n, long p is wrong order, and then I will change it to long p, long n. So the other arguments are 3 pointers to the 3 sequences alpha, beta, and gamma. Gamma is just the power function alpha I to the power beta I modulo p, and now we go on to create the main function. We declare our 3 pointers alpha, beta, and gamma. We choose now the prime p to be 997 and the integer n to be 500,000. The memory is allocated for alpha, beta, and gamma, and now instead of listing all 500,000 elements for alpha and beta, we will list only the first 3, the terms 0, 1, and 2. And the remainder of the sequences will just repeat, so that alpha of 3 will be 8, and then another one will be 9, and then 7. So 8, 9, 7, 8, 9, 7. That's what alpha is going to be. And similar thing will happen to the sequence beta. Now we will make the call to the non-parallel function, the function we just created. And yeah, I warned you that there is going to come a moment when I will decide that n and p should be in the other order. So I'm going to do that now. Yes, I succeeded. So it's n is the second. First goes p, and then we put n. Now we list the sequences alpha, beta, and gamma, and the function is called. We don't want to forget to delete the 3 sequences so that we don't create memory leaks in the case that this ends up being a part of a bigger code. So now we are going to use this class timer. Just before executing non-parallel function, we start the timer. Immediately after the function, we stop the timer. And then we print the time that has passed between starting and stopping the timer, and that's going to be the number of seconds that the non-parallel function took. It now remains to save this file and go to terminal and create the binary. So we will compile this in a very standard way, just the regular C++, and we will use C++11. Now we will execute the code, and at this moment we are waiting for the non-parallel function to finish calculating the 500,000 terms of the sequence gamma. So I will speed up the video because it's going to take more than a minute. It's going to be about 70 seconds. So I will pause the video so you don't wait with me for those 70 seconds. So now you're back. About 35 seconds have been deleted, and now you see that this took 75.8 seconds to execute. We will run this code again. If you do this at home, you will see that your numbers will be slightly different. Hopefully you will not wait for 75 seconds. My Raspberry Pi is running many programs. So for example, I'm making this video. Part of this video is being made on Raspberry Pi. So my test is not perfect in the sense that the CPU is not only working on calculating the terms of the sequence gamma. And then another point to make is 500,000 terms is not a huge number, and the reason why it takes 75 seconds is because the exponents beta are large. They are of order of magnitude 5,000, and I'm calculating alpha to the beta using the for loop. So the loop takes 5,000 steps, and then I have 500,000 terms, so you have to multiply those numbers, so the number is huge, the number of operations, so that's why it's 75 seconds. And this second execution was almost 76 seconds. So we are done with non-parallel code. Now we will move on to the parallel one. Before we develop the parallel algorithm and we write that parallel program, we will first create the simplest parallel program just to illustrate how all cores are used. And in this first program we will just count the number of threads. So it is called threads. So first we have to use API, Application Programming Interface, OpenMP, so we include the header omp.h. And this program will only contain main function that prints this is the first parallel program, and it will count the number of threads. So we first have to enter the block of code that is OMP parallel. It starts with this symbol pragma OMP parallel, and it's very important that those brackets that are opening and closing the parallel block of code are in new lines. So preprocessor directives that start with this symbol, 4 lines crossing each other, cannot end with semicolon and cannot have the open bracket in the same line. So the command omp get number of threads just returns the total number of threads that the computer has. The compiling command is a little bit different. Now, in addition to specifying the name of the output files, so in this case we will call it mfpp, my first parallel program, we have to specify C++11, and we have to put negative F OpenMP, that means framework OpenMP. Once we execute the code, we see that the number of threads is 4. This is not really a surprise, because we know that Raspberry Pi is quad-core. We are still not ready to make our program. Before, we want to learn how some disasters can occur in this parallel programming and how to avoid them. So we will now create one disastrous program. So the next simplest program will result in some very unwelcome behavior. So we will create a function in which every thread will print a message. And this is going to be less than ideal, because threads will write in parallel, so they will compete for a common resource. The common resource in this case is cout, or you could think of it as a screen. So there are 4 threads, 4 computer cores, but only one screen. And now you'll see what happens when all 4 of them start fighting for that very same screen. So now the OMP parallel command also is given the parameter, the number of threads. So with the command OMP parallel num threads, and in brackets we can specify how many threads we want to use in this program. So we don't have to use all 4 of them, and we can actually ask even for 9 threads or 20 threads. Even if our CPU has only 4 cores, some CPUs have multi-threading technology, and other CPUs will just start doing in sequence. So if you ask for 9 threads, then one thread will just assume the role of 2. So each thread will print its own ID number. So when we have 4 threads, their numbers will be 0, 1, 2, 3, and each of them will print the message, my thread number is, and I intentionally am not putting space characters. So there will be no space characters. Every thread will print my thread number is, and then we will use the function OMP get thread number, and this function returns the ID of a thread. So we have this function called printing disaster. We will have a main function that just calls this one. Make sure you save this code, and then you compile it in a very similar way as you did the first parallel program. And now we will execute it several times, and we will have several disasters. So we are now ready to execute it. And so you can see that first one started printing my thread number is, and then second thread won the time with the computer screen and then printed its own message. And when we run programs again and again, so they're in different orders. So sometimes thread 0 is the first one doing the printing. You could see sometimes thread 2 wins and gets to the screen first. So these are some behaviors that should be avoided. So this is, and somehow you may think, fine, I know I should not access screens and printers in parallel. But here is a less subtle mistake. Now this is going to be called, this file will be called even bigger disaster, because this time the bug will not occur because we are accessing something that is obviously a shared resource. This time we are going to have an unwanted behavior called memory race, because several threads will try to access the common variable. They will try to write in the same variable. We will declare a variable res that stands for result. This function arithmetic disaster will return that variable res, and that variable res will be accessed by all 4 threads, and all 4 threads will be writing at the variable. at the very same variable, and the order, so because they are writing at the same time, a disaster is going to occur. So each thread is going to have its own counter. So when the variable I is declared inside the for loop, that variable belongs to each thread. And so each thread is adding 1 to the result over and over again. And now you'll see what happens. When we execute the code, we first get number 4000, but then the second execution gives us a different result, and every time we execute a code, we get totally different result. And now we are ready to create a parallel algorithm for old problem. We will now calculate the terms of the sequence gamma using a CPU that has M cores, or M threads. Raspberry Pi has 4 threads, but we are going to make a general program where we are not going to hard code the number 4 in our source. So for this illustration, I will actually assume that there are 6 threads to show how these jobs will be divided among threads. So if we assume that there are 6 threads, it's not going to be 6. Raspberry Pi has 4 of them. But if there were 6, then their numbers will be 0, 1, 2, 3, 4, 5. The thread 0 will evaluate the terms, will work on terms gamma 0, gamma 6, gamma 12, gamma 18, gamma 24, gamma 30. The thread 1 will work on the terms gamma 1, gamma 7, gamma 13, gamma 19, gamma 25, gamma 31, and so on. Now we will walk over the operations that each thread will perform. So each of them will declare the variable I, that stands for index, like always. That variable I will be declared inside the parallel block of code. And although this variable will be called I for each of the threads, every thread will have its own variable. And we will initialize for thread 0, the initial value of I will be 0. For thread 1, it will be 1. For thread 2, it will be 2. And for thread 5, the number will be 5. It's just the ID of the thread. And in each iteration of the loop, the variable I has to increase by m. So then, because m is 6, so in the next iteration, I becomes I plus 6. And it turns out that each thread should execute the same command. It's time to type this code into Raspberry Pi. We first use editor nano to write the first few characters to the file parallelprogram.cpp, and now we will use the more advanced editor to actually put some code there. We will take the code from the non-parallel version of the program, and we are going to paste it here, and then there are going to be slight modifications. The first one is adding the header OMP H, because this is going to use OpenMP. And we can focus on this function, change its name to parallel function, and so now the modifications will be minimal. So index I the counter I will, each thread will have 1. First, we need to see how many threads there are. So I'm going to copy this I below so that it's going to be part of the parallel part. So first step is to find out how many threads the CPU suggests us to use. So in this parallel block, we will first write into variable m, and to avoid memory race, only the thread whose ID is 0 will have this privilege of writing in the location m. So m is going to be total number of threads. And we should use, if the computer tells us that it has 4 threads, then we should use 4 threads. Although we can use 9 or 39 or whatever number we want, it's usually suggested to use what computer tells the computer is most comfortable giving us, because that's where the biggest efficiency will occur. And so now, inside this parallel block of code, we will declare the variable I. Each thread will have its own I, and the only modification is I should jump by value m, not by value 1. One more modification is that call to the function should be made by appropriate name. And that's about it. We should save the file, compile, and execute, and maybe change this so it prints the correct message. So we now compile with OpenMP flag, and we call the binary will be called parallel. And so now when we execute this program, you will see that the speed will be around 30 seconds. So it's not 4 times faster as you would expect. And the primary reason for that is that my computer is running other processors. So probably one thread was so busy making the videos. If you do not make videos at the same time as making these programs, then you would see that the ratio is closer to 4. So using parallel programs would increase the speed for about 4 times. I'm running this program once again so we can calculate the speed again. It's the same program, but every execution is a little bit different because computers are running so many things. And now this time it was 28.67. And this video is done with programming. Now the question 1 that we asked in the beginning, why are we dealing with multi-core CPUs? And the reason is the speed. The speed of processors cannot increase beyond 2-3 gigahertz for regular computers because the heat is so huge that 10 gigahertz computer would require to be placed somewhere on the moon or somewhere in the space. Now to have number of operations that is above 3 billions, which is some upper limit of how many Raspberry Pi single core can make, is we have to use several cores working in parallel. However, they have to avoid memory races and they have to have different algorithms. Not every algorithm can be parallelized. So that answers the question 2, like what are the things that cannot be parallelized? And now the simplest analogy is not in computer science, but like in sports, in tennis, you wouldn't be the winner if you start playing with 2 rackets. So 2 CPUs is not necessarily better than 1. We just answered the questions 1 and 2. And it remains to answer the question 7. Is it more difficult to make parallel algorithms? This is true-false question. The answer is true. Or let's say yes, it's more difficult to make parallel algorithms. The answer is correct. And we are done.